Alright, welcome to Vodcast 3.6. This is the final Vodcast for Chapter 3, and after spending a great deal of time focusing on streams, we will now turn our attention to groundwater and caverns. The first topic we'll overview is groundwater, and as stated in a previous Vodcast, groundwater is the largest reservoir of fresh water that's readily available to humans. What is groundwater, you may be wondering? Well, it's water that exists in the tiny little pore spaces in between grains of soil and sediment, and it can also exist in narrow joints and fractures in bedrock. But long story short, groundwater is water that's underground. If rock and sediment have high permeability, groundwater can actually flow through that rock and sediment. If we look at the share of total volume of fresh water on planet Earth, we see that ice sheets and glaciers account for about 68.7% of that fresh water. That is water that is not readily available for our use. But groundwater, which accounts for about 30.1% of the total volume of fresh water and 96% of the share for all liquid fresh water, is readily available for our use. Okay, let's suppose you want to dig a well. I used to live in a rural area and we lived on a well, so this is an example I can relate well to. No pun intended. Okay, there was pun intended. Anyway, the main water table in this illustration is the blue shaded region at the bottom of the image. You see the difference between the zone of saturation and the unsaturated zone. The groundwater exists in the zone of saturation, where you can see the water filling in the space between the grains of soil and sediment. In the unsaturated zone, the space in between the grains of soil and sediment is not occupied by water. So let's take a look at this unsuccessful well that was dug. This person tried to dig a well, but it wasn't deep enough, because for the well to function and provide water, it has to get into the water table. So for this well to have been successful, these folks should have dug the well far deeper. Now, as you're probably familiar, not all rocks will be permeable, meaning not all rocks will allow water to flow through them. Impermeable layers such as clay will not allow water to move through them, and those impermeable layers are called aquitards. An aquitard can elevate the water table in a specific region, and in this image, if you look at the length of the aquitard, there's a perched water table sitting on top of it. So the successful well dug here would produce water. But the key point on this slide is that a well is a hole drilled into the zone of saturation to remove groundwater. Let's keep our focus on wells and consider what happens if we overuse a well. Drawdown is the lowering of a water table when water is withdrawn. And when drawdown is significant, you can form a cone of depression. Take a look at the top picture. Suppose you live on the farm shown on the left side of this image, and also note that there's a well dug to the far right side of this image. And both of those wells are successful wells because they're dug far into the zone of saturation. If you turn on the water faucet in your farmhouse, water will come out. But let's suppose someone installs a high capacity well, somewhat nearby your farm, and they plan on pumping out huge quantities of water. Well, let's just say you're not going to be happy, because drawdown will occur as that new high capacity well pumps out large amounts of water over relatively short periods of time. And if that drawdown is significant enough, you can see that the water table is actually lowered, and the cone of depression is centered on that high capacity well. Through well overuse, you would turn on your sink faucet and nothing would come out. I hope this never happens to you, but the overuse of a well can lead to drawdown, and you may see the formation of a cone of depression. Let's also take a look at groundwater contamination. This is a really big deal this day and age, and common sources of contamination include septic tanks, sewer systems, farm waste, and the newest to the list is fracking. Now the good news is there are some natural purification processes that do exist. And to illustrate this, I want to start off by looking at picture B, shown towards the bottom of the slide. Suppose that contaminated water is being released by the house on the right septic tank. And let's suppose that you live in the house shown on the far left. You have a successful well, and very obviously you do not want to be drinking the contaminated water coming from your neighbor's septic tank. Well, I have good news for you. As that contaminated water percolates through the permeable sandstone and sand, it will move relatively slowly, and the sandstone and sand will purify the water. That purification will occur over a relatively short distance, and by the time that water from the septic tank reaches the water table, it will have been purified. Okay, let's consider a little bit more of a gross example now, because not all rocks are particularly good at purification. I won't re-describe the situation, but the main difference shown in picture A is that instead of permeable sandstone, the ground below you is composed primarily of limestone. That contaminated water being released by your neighbor's septic tank will move relatively fast through the cavernous limestone, and that contaminated water will not be completely purified by the time it reaches your well. I know that's kind of a gross thought, and I sure hope you're not eating right now, but with cavernous limestone, that contaminated water will only take days or weeks to reach your well, which is located about 100 meters away from your neighbor's house. Our last consideration in this podcast is caverns. And caverns form due to the erosional work of groundwater. When we talked about chemical weathering, we talked about the action of carbonic acid, which forms when carbon dioxide is dissolved in water. Caverns are typically created in the zone of saturation because you need water present in order for the erosion to occur. Inside the caverns, you can see these really cool icicle-looking rock structures. I'm going to refer to them as rock icicles because I think that sounds kind of cool. But the rock icicles that hang from the ceiling of the cavern are known as stalactites, and the icicles that appear to be growing upside down from the floor of the cavern are called stalagmites. The way I like to remember it is that stalactite has the letter C in the middle of it, C for ceiling, and stalagmite has the letter G in the middle of it, G for ground. Now caverns are pretty cool, and if you ever get the chance to visit one, I strongly recommend you do so. But a similar phenomenon, which isn't quite as cool, can also occur due to the erosional work of groundwater. Shown on the screen is a sinkhole. And just as caverns are formed, where acidic water dissolves limestone, acidic groundwater can erode away large sections of limestone. And if that happens to occur underneath your house, well, the result can obviously be less than ideal. Once that carbonic acid has created a large enough void underneath your house, for instance, the ground below your house can no longer support the weight of the house, and at that point, the house would collapse inward, as shown in this image. Another image to show you, which is actually from Illinois, is the draining of this somewhat large body of water. A sinkhole opened up beneath its surface, and all the water that occupied the space shown essentially sunk down below the surface. Pretty crazy thought to imagine waking up one day and then noticing that the pond or lake in your backyard was completely empty. Okay, that concludes Video Podcast 3.6, and that concludes our content for Chapter 3. Up next is Chapter 4, where we will consider glacial and arid landscapes.